So this is actually like a really nice point cloud that we created from this depth map here by using neural networks. We can see we get a lot more accuracy compared to if you're only using a stereo vision or like stereo cameras to do disparities and then reproject those out to a point cloud. Hey guys, and welcome to a new video in this computer vision tutorial. In this video here, we're going to do point clouds by using deep learning and OpenCV. So in the previous videos, we talked about how we can create point clouds by using stereo vision, and we saw some of the results at the end. But in this video here, we're going to optimize the results. We're going to get better accuracy with our point clouds by using deep learning. And in this video here, we're also only going to use a monocular camera or like a single camera to capture a frame from our webcam. We pass that through a neural network that will then return a depth map, and then we're going to reproject that depth map out to the 3D world coordinate system, which will be our point cloud with a much better accuracy compared to stereo vision. But first of all, we're going to join the Discord server. I'll link to it down in the description here. You come join the channel, chat with us about computer vision, deep learning, AI, and so on. You can also become a member of the channel here if you want to support the channel even more than you're currently doing with a small monthly fee, and everything will go to create more and better quality content here on the channel. So thank you guys. So first of all here, we're going to look at the results that we get from the point clouds by using stereo vision. So in the last video, we had two cameras that is aligned and that the two image planes are parallel, and then we can use disparities to calculate the actual disparity. We went through the theory and stuff like that in that video, and we have also covered it throughout this computer vision tutorial on my channel. But we got this point cloud here from stereo vision where we're just using disparities, and then we're reprojecting that disparity map out into 3D world. But we can see that we don't get like that good accuracy, but we can still like reconstruct our environment with like some noise into our, or like a lot of noise into our point cloud, as you can see in this image, for example. And as you're going to see at the end of this video, we're going to get way more and better accuracy by using deep learning to actually create the depth maps. We cannot run as fast as we're doing it with stereo vision and so on, but we can still run it in a real-time applications and actually like create point clouds that we can use for a lot of different kind of things with really high accuracy. So in this video here, we're going to combine some of the things that we've been throughout this tutorial and also the channel. So we're going to combine the monocular depth camera that we got from the Media's neural network. So I have videos about those. So if you want to know like what we can do with each of these individual things, make sure to check those videos out. They're really nice, they're really cool, and can be used for a lot of different kind of applications and projects. So in the monocular camera depth video, we use the Media's neural network. We just pass in an image, pass it through our neural network, and then we get out a depth map, as you can see at the top thumbnail here. And then we can use this depth map here for a lot of different kind of things. And we all actually like have different kind of models depending on the hardware that you're running and the accuracy you want, or the number of frames per second that you want to get. If we're talking about like deploying these things in a real-time application. So we also had this video with the point clouds as I've just talked about, and then we're going to combine those two things together. So we're actually going to create a point cloud with a monocular camera by using computer vision and deep learning. So this is actually like really nice and really cool. And if we have a GPU, we can run it on. We can even run it in a real-time application or project, and get a really high accuracy on our depth map, as we can see at the top here. And then when we have this accuracy, or like this kind of accuracy here, we can actually like get really nice dense point clouds by only using a monocular camera instead of a stereo vision setup. So this will be some of the results here that we will get from using the neural networks to generate the point clouds. And this is just like a sample of the ones I'm going to show you after we've been through the code. So we're going to go through the code and actually like see how we can set it up, how we can combine these two videos or these two projects that we have done together and create these point clouds. And then at the end of the video, we're going to actually like import it into MeshLab so we can play around with that point cloud and see it from different kind of angles, so we can see the depth in the image and also like how it sees it compared to the depth map that we're creating in our code. So first of all here, we will start in the OpenCV documentation, where I just want to show you the method that we're going to use. So when we have created our depth map with our neural network, then we actually need to reproject that out into the 3D world, because we only have 2D information in our image, where we actually need to reproject those out as well, combined with the depth that we get from the depth map. So we actually have a function implemented in OpenCV, and we're just going to use that. But we need to make sure that we have the right like data types and data structures that we pass into that function. So if we just go down here we will find the function, and then you can see like what it takes as input parameters and what is the output, and then we can use that output to actually like generate our point cloud. So down here we should find like it is called this reproject point. So we're going to have this reproject image to 3D. So this reprojects a disparity image to 3D space. So we can actually like have our depth map or our disparity map and combine that to an actual like disparity map, and then from the neural network, and then we can use that to input as this in this function, and then we can just get the 3D space of that disparity map, which we will convert to a point cloud later on. But here we need to make sure, as I talked about in the last video, that when we actually use these things here, we need to make sure that we have the exact right data type that we're using. So in this video here, we're going to use 32-bit floating point disparity image. So we need to convert our depth output from neural network to that data type, and then we can actually just pass it into this function together with the Q matrix that we get from our perspective transformation matrix as well, and then we can just reproject those points out into the 3D world. So the output here will actually like be this output 3-channel floating point image of the same size as the disparity. So this will just mean that we get out this format here, so we can just read it down here. The function transforms a single channel disparity map to a 3-channel image representing as 3D surface. So this will be our point cloud that we can then later together with the color. So we can go in, take the individual colors from the image of those points that we actually like project out, and then we can create a nice structure or like a nice texture in our point cloud as well together with colors, so we can try to reconstruct our image in 3D world with the colors as well. So that is for each pixel, so we get an X and Y, and then the corresponding disparity, which is the D, so this is the disparity of the XY here, and then we'll get it out in this format here. So we have the XY, and then we have the disparity together with our homogeneous coordinate. So this is the function that we're just going to use, combine it with our neural network. So let's jump straight into the code here and see how we can actually combine these things with where we combine OpenCV, computer vision, deep learning, and the functions that I just showed you in the OpenCV documentation, and then how we can generate a point cloud from our reprojection of our 2D points with our depth map or disparity map. So first of all, we're just going to import NumPy, CV2, matplotlib, and so on. Then we have this function here to actually downsample our image, because if we have a too complex image or we have like too large dimensions of our image, then we'll just create like a too large point cloud, and we can't really load that in or do anything with that because we just have too many values, and it actually we still get accurate and good results by downsampling our image. And in this video, we're going to downsample our image by a factor of 3, and we will still get really nice results. So you should definitely downsample your image as well to generate like a smaller point cloud, but you will still get like a lot of points and a lot of information in your point cloud still. So this is just a function that we're going to use to downsample our image. Then we go down here and actually like set up the neural network part. So we're going to have a path here or directory where we have these two media models. So we just have a path here to our models. I can just show you them here. So we have our directory, and then we have our models, and then inside of our models we have the medias 2.1 large model and the small model. In this video here, we're just going to run it for the large model because we're just going to load in one image, process that image, and then generate a point cloud for that image. So we won't really care about like a real-time application or like how fast it's running. We just want the best accuracy as possible. But if you're going to run it on a real-time application, you can use the small model as well, but your accuracy will lag a bit. But if you have a GPU, you can run it on and use OpenCV together with your GPU. I have videos about that as well if you want to know how we can set up and install OpenCV with GPU support, which will speed up our process and our OpenCV applications by a lot, up to 30 times. We can even like speed up our applications up to 30 times. So make sure to check those videos out if you have an NVIDIA GPU and you want to use that. But here we're just going to load in our model with our DNN module from OpenCV. So we're just going to have this model variable here. We're going to set equal to CV2 DNN because we're using the DNN module, and then we have a function inside of that module that is called readnet, and we just specified the path here to the model that we're going to load in that we can then use later on to pass our image through. We're just going to have an if statement here checking if our model is empty, and if it's empty, we could not load in the neural network, and we should definitely check the path, because one of the most common errors is that we're not specifying the path correctly, and then we can't load in the model, we won't have anything in our model, and we won't get any results at the end. Here we can set the preferable backend if we're using a GPU for our application. So we just set these two here, you'll just uncomment these and they will run on the GPU instead of the CPU when you're processing and even like passing your model or like your images through the neural network. Here we're going to have as a file stored, so we're going to load in the Q matrix from the camera. So we will need to calibrate your cameras first of all, so we actually like get information about like the intrinsic parameters of your camera, and then you can calibrate those and get the Q matrix, which is just like the perspective transformation matrix that we need to pass into the reprojection function later on. So you need to do camera calibration first of all. I have videos about all of it. You can just go into my GitHub, find the calibration scripts. You can just pass in your images, run the calibration script, and you will get everything stored in this stereomap.xml file. And then you can just load in the Q matrix like this way. So we're going to open up our webcam here, and then we're going to read in an image from the webcam, and we're going to store the image that we read in from the webcam in this im variable. Then we're going to start a timer. We won't do that in this application because we're just going to run one image through, process one image, and then generate a point cloud for that. First of all, we're just going to show the image, so the image that we're loading in. We're going to downsample our image by a factor of 3 with this downsample function that I just talked about. Then we're just going to show the image here again so we can see like what information and what dimensions do our image actually like have after we're downsample our image, because this is the image that we're going to operate with and process and pass through a neural network and so on and do all the operations on. So first of all, then we're going to convert our color from BGR to RGB because this MEDAS neural network takes RGB channels instead of BGR. So OpenCV loads in our images in BGR, so we need to convert that before we pass it into our MEDAS neural network. We get the image height, image width, and also the channels of our image that we can then use later on. So now we're going to create a blob from the image before we can actually like pass this blob through the neural network. And we have different kind of like pre-processing parameters that we need to take into account before we're passing it through the MEDAS neural network. So these are just default values that we'll need to use, and this is just like how the MEDAS inputs should be. So we can either use the large model or the small model, and the only difference is the image dimensions. So for the large model, we pass in an image that is 384 by 384. So we actually like square the image and crop out some of the information. But this is just the input dimensions that this MEDAS neural network here takes. And we can also use the small model here, which is just like 256 times 256. So we'll just like, it's just like kind of like a downscaling by a factor of 0.1 or like 1.5. So we can speed up the process by using this small model here compared to the large model. But in this video, we don't care about like how fast it runs. We just want as high accuracy as possible when we're generating our point cloud. So that's why we're using this MEDAS version 2.1 large model. And we can also see that we need to normalize our image first of all, and then we also have a mean subtraction where we just need to pass in these values because this is the way that the MEDAS neural network is trained. Then when we have set our blob here from our image, we need to set that blob as the input to our model. We're just going to do it in this way. So we have model.setInput, and then we just pass in the blob that we want to set as the input. And now we actually have everything set up, and we can just call this model.forward. It will do a forward pass of our blob or our image through the neural network, and then we will actually get the results out in this output. So this output here will actually be our depth map that we can use later on. First of all, we need to resize our depth map to our like original image dimensions, because we actually like squared them here before we're passing it through this blob from image function. So just to get the original dimensions out again, we're going to take the output, we're going to resize it, and then we're going to normalize the output here, as you can see. So we're going to normalize it to values between 0 and 1, and then we're going to display that because we actually need this. And we also specify here the data type. So we set the data type equal to CV_32 floating point values, because we need that data type when we're actually going to pass it through this reproject image to 3D later on. So here we're just going to show with the matplotlib here, we're going to show our output, which is just our depth map generated from the neural network. So when we have our output or like a depth map here, we can actually like use that to reproject our points into 3D. And we do that by using this function that I showed you in the OpenCV documentation. So all of our 3D points, or actually like point cloud before some post-processing, will be stored in this variable here. And then we just pass in the output, which is the output from our media's neural network. We have normalized it, and it is 32 floating point. So this is our depth map, this is our Q matrix, and then we can set like if we want to handle missing values. So if we're not able to actually like reproject our points into 3D, then we can either like set the depth equal to I think it's 10,000 as default in OpenCV if we're using handle missing values, but we're not going to do that. So if we can compute some of the values and reproject those out to the 3D world coordinate system, we're just going to reject them and we're just going to throw them away, which is often the case that we want to do, because the other thing doesn't really make sense just to take like an arbitrary number and set that as the depth. We'll just throw out those values instead. So now we need to get rid of the points with value 0. So if we don't have a depth in our image, we're just going to filter those out. We're going to generate this mask here for a map, so we can actually like take only the points where we're able to actually like reproject our image with the x and y coordinate, and also the c coordinate for the depth in our point cloud. So here our final output points will be the point clouds here in the 3D, which is the output from our reprojection. And then we're just going to take the map here, which are mask of the map. So we take all the values that we're actually like able to reproject out with a corresponding and correct C value. We also need to take the output color. So we want to get the corresponding color for all the points that we're reprojecting out. So we're going to take the original image, and then we're just going to take the exact same points as we did in the point cloud. So we're going to take the colors of that image with the corresponding points from our point cloud, so we can actually like create this texture later on when we load it into MeshLab and play around with it, so we actually like reconstruct our image with the corresponding RGB values as well. So now we actually like have everything. This will be our two outputs. So we have our output 3D points. So this is our point cloud, and this is our point cloud with the corresponding colors to it. So now we're going to create this function so we can actually like create our point cloud file. We're going to use a format called PLY. We don't really need, this is just like how we can set it up. You're just going to use this function, but we need to reshape our colors first. So we'll put that in the end. And then we also have these vertices, which will just be our like a horizontal stack of these vertices here, and the colors that we're passing into this create output. So these will be the point clouds, or like the X, Y, and Z coordinates. This will be our colors and the file name that we pass in. And then we're just going to do a horizontal stack of those values. So our format here will just be that we have an X value, we have a Y value, and we have a C value, and then we have a red colored channel value, and we have a value for a green channel, and we also have one for our blue channel as well. So this is all the information we need. We need X, Y, Z, red, blue, green to actually like reconstruct our image into a point cloud only using a monocular camera and neural networks. Then we're just going to open up a file, and we're just going to write out all of these things, or like all of the point cloud, to our actual like file, and then we're just going to save it here at the end. So now we're just going to create this, or like use this function that we just declared up here. So we're going to have an output file. We're going to call it reconstructed mono-NN, because we're reconstructing our image with a monocular camera and we're using it with neural networks. Then we're going to generate our output here. We pass in the output points, so our X, Y, and Z coordinates from our depth map. We're going to take the corresponding colors for our point cloud and our output file name, which is this name up here. And it will generate our output file in the same directory as our Python script here. It will generate that file. It will release the capture or a webcam, and it will store all the windows here that I had opened up with OpenCV. So everything you need to do is actually like just go into my GitHub. I'll link to it down in the description here. You can just go into my GitHub, just take the Python script here, run it with your own like a webcam or like your own camera. Just make sure that you have like the models in the same directories as me, and then you just run this Python script here, go into MeshLab, import the point cloud, and you can do everything that we're going to do now. It's just run the Python script, and you have everything up going. You can play around with it yourself. So now we're going to run the program here, and I'll just stay in the front of the camera, so we're capturing the first image. So this will be an image. When I hit Q, we would like to downsample our image, as we can see here. So we're reducing the dimensions. We're losing a bit of the information here before we actually create this blob, but we need to do that because else we'll just create too large of a point cloud. And then when we hit Q again, it will like to create this depth map here by passing it through the neural network. So we can see me in the foreground here. There's a lot of like brighter pixels. So the brighter the pixels are, the closer the object is to the camera. And like here in the background, we can see all these dark values. We can even see my face here is in front of my body, which is correct because these pixel values down here is a bit more gray compared to my face, for example. So my face will be in the foreground, and then a bit further away there, my body will be there, and then we can see the background here at the back is totally dark because it is the furthest away from the camera. When I hit Q here again, we will actually generate our point cloud, and then we can go in, load it into MeshLab. So if we go into the directory here, we have now generated this reconstructed mono NN file. So here we can just see the X, Y, Z value, red, green, blue, and then we will get all of the coordinates and all of the colors here for the point cloud that we've created. So we have all the X, Y, Z values here, and then we have the color values over here to the right. So if we go up at the top here, we almost have like 5,000 different kind of elements in our point clouds. So this will be a point cloud of 5,000 elements with all of these values here for each point. So now we've opened up MeshLab here, and we're actually going to import our mesh. So we're just going to the directory where we just saved this file. So we're just going to open up this reconstructed mono NN. When we open it up, we can see that we get this point cloud. We just need to zoom in here a bit because it's a bit far away. Just keep zooming in. We can see all the depth pixels here that we get in our point cloud. I'll just rotate it a bit here and zoom in further so we can actually see the image and what is going on. And then we also need to orientate it correctly. So I'll just flip it around here. But here we can actually see the point cloud that we get. So this is me, the face in the foreground. We can see that my face pixels is actually in the foreground as we saw if we just take up this depth map again. So all the white pixels is actually my head, and then my body here is a bit further away because the pixels is more grayish, and then the background here is the furthest away that we can get, and that's why we have all these values here so far away from my actual face in this point cloud that we have created. So this is actually a really nice point cloud that we created from this depth map here by using neural networks. We can see we get a lot more accuracy compared to if you're only using a stereo vision or stereo cameras to do disparities and then reproject those out to a point cloud. So this is a really nice point cloud that we get. We can see that if we orientate it like this is just a fully reconstruction of our image that we actually capture with our camera. So we only have 2D information with our camera, monocular camera. But when we're using deep learning, we can get the information about the depth as well, and we can reproject those out and create an actual point cloud. And we can see that this is a fully reconstruction of the image. We even get the TV here at the background and we even get here as well. So if we just play around here with it a bit, we can see that all information here, my face is in the foreground, my body here is a bit further away, and then we can see all the values here at the background, which was the dark pixels, are all the way back down here, and these are just the background pixels here. So this is just really nice. We can use this for a lot of different kind of applications and projects, and we're even going to create more videos where we're going to do even more post-processing of these point clouds that we're creating. We can even try to do it in real time and try to create point clouds in real time as well, or reconstruct whole environments by taking multiple different kind of images, reconstructing whole environments instead of just one image here, as we can see. But this is a really nice result. You can just take the Python script, play around with it, and do the exact same thing as I've done here. So really nice result that we get by using OpenCV and deep learning together with only a standard webcam, a standard monocular webcam. So thank you guys for watching this video here, and remember to hit the subscribe button and bell notification under the video. And also like this video here if you like the content and you want more in the future, because it just really helps me and the YouTube channel out in a massive way. I'm currently also doing this deep learning tutorial if you want to know more in detail what deep learning is and how we can use deep learning to actually create a model, train it on a data set, and how we can get the outputs. So I'll link to that deep learning tutorial up here, or else I'm just seeing you in the next video, guys. Bye for now.